reconstructing cortical current density by exploring spareness in the transfer domain. But let me give you the basics. What is the basic target here? Like you know, in EEG and MEG, what we are trying to get, we are getting the signals with the brain activity, the electrical and magnetical signals, and then with these signals which we are getting from the skull, scientists are trying to diagnose that if we have activity, if we get the EEG signal, then how the signals are creating inside the cortex, inside the brain. How is the distribution of the signals which are creating inside? That is called electromagnetic source imaging. So in my presentation, I will just discuss a basic what is EEG, MEG, what is the application, what is electromagnetic source imaging. Then there are a few methods which I am going to discuss how we will go for electromagnetic source imaging. So we have sparse source imaging, then sparseness in transfer domain, then this is in sparse source imaging there are 2 or 3 methods which are already given. Weighted MNE is minimum normal expectation, C Lauretta and BBC XCD. So I will compare these things. So the thing is that when we are getting high quality EEG and MEG signals which are excellent temporal resolutions in millisecond scale, so it is helping to study the human brain activity very precisely. Okay, basically EEG is nothing but what happens when we do some activity, some electrical and magnetic signals are generated by the neurons. But there are millions of neurons, so what happens, whatever signal we get here is not created by a single neuron, it is the activity of like millions of neurons, like suppose this place, and the signal which is called in the same phase, it amplified due to the interference and then detected, because single neuron will create like a nanosecond and we can't detect that nano millivolt or something like nanovolt. So we can't detect it, but when millions of neurons generate a signal and the combined form, we will get it, and that is like some millivolt, the EEG signal is in some millivolts, which is not due to one neuron, which is effect of so many millions of neurons.
M is the million? MEG?
Oh no. EEG is electrical encephalography, MEG is magnetoencephalography. So electrical and magnetic signals. So electrical is in volt and magnetic signals are more in form of either current or magnetic field. It depends how you are measuring. Now when we talk about ESI, it is a technique to reconstruct cortical electrical activity from external surface. From external surface we are getting EEG and EMG, and we are trying to create a distribution of source. It means distribution means where the dipoles are located. If we imagine that it is created by some dipoles, so how the signals are distributed along our brain. So this is called imaging.
What's the meaning of cortical?
Cortical is related with brain. So the cortex is, you know, the, let me show you the. If I talk about this layer, so this is skull.
Layer of brain.
Brain, yeah. Means the upper part is skull. Then it's called skull. Skull has outer layer and inner layer. And the portion you see like this of the brain, I am not good at making the picture. This is called, you can say, cortex, or this is called this part, the inner part. Okay? So cortical activity means brain activity.
So you are using the ESI to infer the activity, the hidden variables, like.
Let me tell you what happens. Suppose I move my hand, or any brain activity we are thinking. So with any of the brain activity, this is our brain part. So some signal will be created from here, 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 here. What we are getting? We are getting from outside, from the upper part of skull. But we don't know how the signal has come. So from the EEG signal, we are trying to find out the distribution inside the head. This is called ESI, electromagnetic source imaging. How it is distributed inside the skull. Let's say one dipole is here, one dipole is here. This is our assumption. So this is called distribution of the signal or cortical things. This is called ESI, electromagnetic source imaging, and it is called inverse problem. Inverse problem means we got EEG signal, and from first the signals are generated here. We receive the EEG. From EEG we are trying to go back to the distribution. That is called inverse problem. I hope you understand the basic thing. Okay. It is a non-invasive technique. Non-invasive means we are not putting anything inside the brain. So the exploration of human brain function using inverse solution is applied to neuroscience research for studying the working brain and clinical diagnosis of severe neurological diseases. That's why this inverse problem technique is very important for just find out how the signals are created inside the brain. Yeah, next. Now the problem is a simple thing. If I say, suppose I have an equation x plus 2y equals to 1. How many parameters or how many variables we have? 2. But equation is 1, which I got by some experiment. Do you think it has a unique solution? No, because when variables are more, then you can't find out the exact solution. You need the same number of equations as variable to find out the unique solution. The same thing is here. We have in EEG, MEG inverse problem, we don't have unique solutions. The reason is there are millions of neurons. But when we get the EEG and MEG signals, we have limited number of electrodes. So it means the output signals are less and the number of neurons are in millions. So we can't have the unique solution. But what we do, we make some models. So favorable inverse solution can be obtained by implementing some source models. It means we assume we have some models. If we use that models, then only we can find out the inverse solution, which is the kind of approximation of the exact one.
Sorry, the solution for, what do you mean the solution here, the unique solution?
Suppose we are looking our brain from the top, okay? Now I got a EEG signals. So what I can find out the exact result that signals dipole's location should be like this. Okay. This is one unique solution. Another unique solution may be like this is the different distribution.
Oh, you mean that the solution for choosing?
Yeah, from where the signal is exactly generated. I have to find out the exact distribution that suppose I move my finger or my hand. So how the signals are generated here? What is the distribution of signal inside the brain? So that's called inverse
We
technique.
have limitations and sensors.
The thing is, yeah,
The
sensors
number of the sensors.
128. This is right now what we are using is 128 numbers of electrodes. So we can get 128 equations, you can say. But neurons are in millions. So how we can find out the exact solutions? So for that one we have to model it. And those I am talking about the models, that there are 3-4 models.
Excuse me. Each sensor can cover how many?
Yeah. It covers like in some square inches. Whenever we talk about electron, how much it is covering, it covers in some square inches. But you can't count the neurons because it's like cells.
Okay, but we don't have any estimation for the how many neurons we have in the.
The thing is that
sensor?
when we will Pardon? Can you say again, please?
I mean that we cannot estimate how many
Neurons.
yeah, we have for each sensors.
Actually, when we are finding out the distribution, we are assuming, we are not thinking about neurons, we are thinking about some dipoles, which is imagination, that some dipole is here, some dipole is here, and we can assume, we can reduce the number of dipoles, assumption. It's just an assumption because we can't think of millions of neurons, we can think of dipoles. By reducing those numbers, we can reach to some unique solution.
What's the meaning of dipole?
Huh?
What's the meaning of dipole?
Dipole means when you are getting some voltage from some point, some potential, so you can assume that some dipole is there. It's coming out from some dipole.
Can I just confirm it too? So you have like a matrix like A, which is like fat and short, and then you have like X, and then you have a measure of like B, which is for each point you have a measurement.
Yeah, yeah.
You have a lot of B's.
Yeah, this is known as phi, and this is known as S. If you are talking about phi means what we are receiving at the output from the EEG. This is kind of some A matrix with some gain matrix.
So because this is fat and short, so you have if you do elimination, you have free variables here, and you have identity matrix here. So it's free variables, you can set everything.
The thing is that what calculation he has done is little bit different from what we are talking about. But what model I am trying to give, that because for unique solution we have to follow some model. And let me discuss some models and then I will go to the mathematical part. But one thing is clear, that when we are assuming the distribution, we have to reduce the number of dipoles, otherwise we want to get that unique solution. So one basic source model which was given, the earliest one was equivalent current dipole, ECD model. It assumes EEG, MEG signals are generated by one or few focal current dipoles. If you read this line, I think your concept will be more clear. That in this model, we are just assuming that we have some focal current dipoles. It means this, if some voltage potential is coming from this area, we are not assuming there are 10 or 100 dipoles. We are assuming some focal, we can concentrate it at one place and take one dipole. It's like that. Another source model is distributed current density, which is the main topic. Dr. Ding is following this model, a special version of this model. It reconstructs neural sources by finding the most probable current distribution in predefined source space. Here, all the means how we will take the in this model. What he is doing, we are predefining some source space, and then we are creating kind of probable current distribution in this model.
What's the difference between these two models?
If we talk about first model, that is assuming a dipole. Dipole is kind of creating some voltage.
Okay. In the first one, you're thinking about, for example, the problem is we have, for example, it's a 0-1 problem in the first one, and in the second one is something like distribution.
No. The thing is that, look, basically what we are trying to do, we are trying to find out the source of potential and current. So one model is given in terms of dipoles. And when he talk about dipoles, dipole means what he assumed. Suppose there are 10 or 15 dipoles, but he is assuming a concentrated or a focal current dipole at one position. Focal means, like light is distributed light is coming, we assume it's coming from single point. Similarly, if potential is coming from so many dipoles, we can assume that there is a single dipole at some location. But still we can find out a distribution. This is first assumption. Another assumption is DCD model, distributed current density. It means he is assuming that current density is distributed in a particular area, like we have some gray area. I'm just missing the name. So in the next model, we will assume that the current is only in that location. Current is coming from that location only. So current means very like in my nanoamperes. But he is assuming that there is some neural source and finding the most probable current distribution in predefined source space. So we have some source space, we assume some source space, and we put some distribution here that current is coming like this. So it's a model to get the unique solution.
So is that like assuming two different kind of sources? One is like current source, the other is
No, sir, these are different models. So
yeah, but I mean model in the sense that you assume there's some source to generate that whatever image, right?
yeah. Some source which is generating EEG and EMG signals.
So are they using both signals, or like they do? I mean, when they have a EEG and MEG, do they like? I mean, trying to find this. I mean, a source that will map to these two images at the same time, or like just do one EEG or do one MEG?
No. At a time we either take EEG or MEG.
Okay.
Okay. So suppose we get EEG signals. So now we have to think that we are getting signal here.
So there's they never do something like that. Like why they don't do that? I mean, it's kind of weird. If you have both images, I guess you can basically like you have more equations and
Yeah. So
you
if,
probably can.
the thing is that for millions and millions neurons we can't find out the distribution. We can just find out the few locations that from here this is the source of volt potential or current. So when we distribute, we can't think of millions of neurons. We can think of some dipoles here or some.
No. I'm talking something else. I mean,
Sorry, I
did
didn't
you
get it.
did they try to do the inverse problem for both images at the same time, or like you said like just either doing MEG or EEG?
Yeah, they are doing, and after doing, they are trying to. It's like a let me give you one example. Suppose we are doing some estimation. If you have studied numerical analysis, so suppose we have a curve, okay? Now we have some data. We are trying to fit into this one. So we take different types of norm. So in that thing, what will happen? If somebody can take it as a straight line, somebody can take it like this kind of curve. So we are just approximating that thing, and then we find out the error, that which model has minimum error. So in the same manner, different models they have created, and then they are trying to find out the accuracy, that from this model can we get the same EEG or not. Are you getting my point? Means from EEG we take this model, we assume this model, and from this model we will try to calculate the same signal. Is it exactly same or it has some error? Then we take the second model, we will find its accuracy. So they are both have different accuracies. And the third one which Dr. Ding is proposing, it has some different accuracy. So from EEG, we go for inverse problem. We find out the distribution. From that distribution, we are again trying to get the EEG signal, the potential, the calculation. In that calculation, if we are find more accuracy, it means that model is more accurate. So,
but like for the model, like whatever you're using, like do they try to match both EEG and MEG signal, or like?
yeah, for both. Yeah.
At the same time, like just let's say pick one of the model, like maybe the dipole, and then they of course they want to try and find the distribution of the dipoles so that you have that EEG signal. Like,
yeah.
Do they like at the same time want to find that model such that both EEG and MEG matches?
Yeah.
Okay. I just want
Let's talk about cortical current density model. This is the most used model in is cortical current density model. It assumes that the possible source space is on cortical gray matter. It is a part of our brain, and its element source are constrained by their perpendicular orientation to the cortical sheath. Now it is an assumption. As we didn't see how it's created inside, so this is an assumption. Suppose this is our cortical space. Okay, so assume that the possible source space means from where, whether it's dipole or current source, it is the cortical gray matter. I think you might have heard about gray matter. It is inside our brain, skull, and its element sources are perpendicular to this one. So dipoles are like this. So this is an assumption for cortical current density model.
How is this assumption affect your model?
Oh, okay. Whatever I have studied in this paper, according to that, here is the answer in the last line. Here, the unique CCD solutions are generally solved through regularized linear problems. So it is converted into a linear problem. That's why he used these assumptions. And how it is done, I will show you a little bit mathematics, how it becomes linearized.
If it's not perpendicular, then you cannot use the linear.
You know, if it is not perpendicular, you know, for a dipole, if I remember, suppose I have to find out the potential formula for due to a dipole. It's 1 pi 4 pi epsilon 0 AQ r squared cos theta, where theta is this angle. So with the perpendicular thing, I hope the potential becomes 0 in this direction. One component becomes 0 and one component becomes, like when theta is 0, it becomes maximum 1. On the other side, when the theta is 90, it becomes 0. So I think by doing this, the potential has we can assume that it can be, we can find out a linear relationship. If angle is not perpendicular, then it may be create some non-linearity. That's the formula for potential due to dipole. Similarly, if we talk about some current value, so I think this, because of this theta, he assumed it at 90 degrees.
We get the sensor and
He assumed that all the sources are on gray matter. Suppose this is our area, which is called the gray matter, which is inside our brain, and he assumed all the current sources are dipole perpendicular to this one, and he said by assuming this one, the solutions are solved through regularized linear problems. I will tell you what is regularized linear problem. Because of this one, why this is, when I went to the mathematics, it's not very clear that why this statement is there, but this statement is the answer why he took it as a perpendicular, why he assumed as perpendicular.
yeah, I have a question. The gray one is the exactly gray inside the room.
Let me show you the picture if I remember, if I get it immediately.
Or just the sensor above the.
I can show you this picture. This picture defines all the parts of this one, and the gray part where he is assuming the dots. So skull.
The gray one is that.
If you see the just a second, let me check. Miss, I was thinking of this one, the top part, because here he is assuming that dipoles, distribution are dipoles. But did he mention some gray part here? Where he is assuming the dipoles, that part is.
It means that
Yes, somewhere inside.
The
Inside,
bone?
yeah, inside, yeah. Not outside. This is skull. inside the skull there is skull. So I think the top part of skull he's assuming as
But
gray
you said
matter.
that that's why it's invasive.
Yeah, invasive. Yeah, invasive means we are not placing any
Exactly,
needles
yeah,
inside.
exactly.
But we can assume that signals are coming from some part.
Okay.
So the signals which are coming from gray area.
We don't have any other signals from the bones or maybe the skin.
This is assumption, as I told you, because if I talk about because the conductivity of brain inside is not same, so we have to assume for this model that conductivity is similar. We have to assume that the signal which is traveling equal distance. Are you getting my point? Because signal may be created here, 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 but we are assuming that it is equally distributed. That's why he assuming that suppose this is the gray matter. So all the sources are here and perpendicular to this one. So this is a kind of assumption to do the mathematics. You know, when we do the mathematics, we have to do some assumptions.
But no, I mean that's the mathematics.
Yeah, to create it means
how they can just remove the signals from the bone and skin from the.
in my opinion, from the bone, I think if I talk about biologically, from the bone the signals will not generate it. It should generate somewhere inside which it has some liquid layer from where the signals are creating. And that's why he used the gray matter. I don't know the exact what is the physically gray matter is, but it's some kind of layer which has all the neurons which are creating, and it's like along the surface of our skull. So we have to find out the distribution from where the signals are generating. And to make it linear, we can solve it using regularized linear problems. Okay. Sorry. Okay, and what we will use, these are few methods which we will use for every time. Like one is minimum norm estimate. When we are estimating something, we are getting the approximate model of something, then we have to use some algorithm, and out of which one is MNE, minimum norm estimate. We can use L1 norm, L2 norm. You know, what is norm? Is everybody know about this one, or I have to tell?
Are you saying the distance between your
estimation
value
and exact value? Like suppose this is my estimation A1, B1, C1, A2, B2, C2, and this is suppose the exact value A1 dash, A2 dash, B1 dash, C1 dash. So if I just find out the difference of this one, this is L1 norm. If I take the square and under root, that is L2 norm. One is weighted MNE. In weighted MNE, we will multiply everything with some weight W. Another method is low resolution brain electromagnetic tomography. I always forget its.
How can find the weight for that? Weight. How can find the weight?
It's just written in the equation in terms of Wij. So weighted means some W. But how to find, I have no idea. It's just written over there.
I mean, you don't know how can just find the weight?
How to find out weighted? Because this is not the method he's using. He's using either L1 norm or L2 norm.
Okay.
And he's comparing that somebody did using weighted norm. So I didn't went through that paper.
In this method they use the WMNE?
No, he's using the L2 norm. He's using using cortical current density model with either L1 norm or L2 norm.
Okay, and now what's the weighted MNE?
Weighted MNE means he can multiply in case weighted is multiplying by some W weight. I will just show you the equation. Okay.
You are saying the weight is for the difference between estimation and the
exact what value we read, we get experimentally we get this one, and this is our estimation. So that the difference of matrices.
You want to minimize the error.
Yeah, minimize that.
The
Yeah.
related method just tell you which component is more important.
Oh yeah, I got it. Yeah. Actually, I didn't care about in the mathematics we're multiplying by W, so I just assumed that okay, this is multiplying. Here is the mathematics. Actually, I was trying to insert the equations, but I am not able to do it. So, if the source space and recording space both are discretized, discretized means we just assume that we have fixed recording place and fixed source space like this. This is discretized source space. And the relationship between electric fields outside the head, this is outside the head, say this is phi, and the current sources as say S, say S1, S2, S3, Phi1, Phi2, Phi3, it is distributed like that. N is the noise which is added during the signal when reaches from here to here. So phi, this is the external one, it's gain matrices. This is the linear equation, and this linear equation will come when we will assume that everything is on gray matter and the dipole is perpendicular to this one. Then we can use this linearization equation. Phi denotes the potential at n scalp electrodes, and S is the vector consisting of n dipole moments defined on n triangular elements of CCD model. Whatever CCD model we have assumed, this is S. So it is a vector of, or we can say matrix of all the sources. A is the gain matrix. It is M by N. And S is source. As I told you that source N is number of dipoles, because you know N number of dipoles are much more than the number of electrodes. Number of electrodes is just M, so M is much less than N. In inverse problem, because there is no solution, so we have to use regularization scheme, either using L1 norm or L2 norm. So how we use the regularization scheme? We have to minimize this is W2, this is L2 norm, and here the phi minus AS W2 norm should be less than some value, say beta. Phi means what we receive, and AS, S is signal. So phi minus AS, if you see this equation, it's just but some noise. So in fact, if noise is not there, these should be equal. So it means my approximation and my calculation, the exact value and the approximate value, they should have the minimum thing. It should be less than some beta. Yeah.
How you can find the A here for this problem?
And my question is, what is the W here? Because you can, for example, set the W equal to 0 and you get a minimum.
No, W, I think it is find out using the normalization MNE mathematical process when we do. We have to find some minimum W. Sir, am I correct? In this one, W we calculate.
W is the weight, right?
Yeah, this is the weighted, yeah.
Yeah.
So W, I think it's we have to calculate using some mathematical technique, which I don't know, but it should be.
Find out the W from your model, or you must find from the optimization and find the minimum.
I think when equation goes like this, he was trying to do like this, S equal to phi A inverse matrix, and then he was putting it there. I saw that solution like this. Then
A inverse.
and somewhere I found a solution, but right now I don't remember where I kept it. So using that, but this was a regularization technique. Means the thing is that little bit I messed up with the mathematics, but this is a regularization technique by which he was saying that we can find out, we can minimize this one.
This is more approximation than regularization. This is more approximation, not regularization.
Yeah.
This is just saying you need to find the noise to approximate the measured signals. There's nothing about regularization.
Either that.
I think the norm is regularization.
The first one.
Okay, WI, he has defined WIA here, yes. W is he's explaining that it's a n by n diagonal matrices, and it can be calculated like 80.
They will use a matrix.
Yeah, it's a diagonal matrix defined as this one.
I have a question.
And
A.
now the question is how I have to find out A.
Can you explain the first term? The regularization part.
Pardon?
The mean WS.
This is the what it is called. We have the signals, weighted signal, and we are finding the norm expectation, minimum norm expectation. It was used in that manner. Like we have phi signal in matrix form. Say this is what we are getting from m electrodes.
So you are saying the S here, norm of S here should be as small as possible.
Yeah.
But
It should be less than a minimum value. It means the error should be less, minimized.
there are two separate optimizations.
No, the second is constraint.
Let me write down what he has written.
Why not such that or something like that? But you just mix it out.
And we can use the L1 norm. For L1 norm, in place of 2, if we put just a minimum of W as there. It should be 1. Here in the paper he has written 2.
No, that's why it's 2.
No, it doesn't matter.
It means for this error should be less than a very small value, then by minimizing this one.
All of it is hats.
Yeah, actually this is a matrix, that's why, or you can say it's a vector, that's why it is putting like hat or cap, it's not clear. It's not cap, it's kind of like a straight line, I think so. It's vector. So this, they use this one like
Yeah, how about A?
yeah, how about A? Yeah, I didn't think. A is again just written here. A equals to A1, A2, AN is a gain matrix. I assume as it is.
And how about A1, A2?
That's
Yeah,
what they
yeah.
did in this paper? Or
Pardon?
That's what they did in this paper? That's what they proposed or like
No. He didn't
some
propose. His proposal, he has to propose. Sorry.
So this is some prior work or like
No, this is prior work, yeah.
Okay.
he used this method and he said that this sparseness should be in a transform domain. Means he is trying to transfer, like we use the frequency domain, he used some transform domain to
Sorry, I didn't get about the A1, A2.
just let me think over it.
Oh,
And,
okay.
okay. So what will happen now? I assume as it is okay. This is there. So I didn't think why it's so. So give me some time, and I will try and go for it.
I guess like I don't know. So it should be from the measurement. I mean, your A is some kind of assumption.
He's saying a gain matrix. According to him, it's just a gain matrix. And in gain matrix, he said that why A is putting like when signals come from here to here, S is here, phi is here. So naturally, there should be some proportionality constant. How it comes, I didn't think of it. But what is A? What I'm thinking from source, as signal is creating, here it's we are receiving phi. So there should be some loss or there should be some gain. So he has put it as gain.
How big is N?
N is noise, which is
No, the big N is not the small N.
oh,
Give me the number.
capital N are number of dipoles or sources.
So it spread the whole weight matter.
Yeah.
What did they use in practice? Like
What?
in experiment, for example, the simulation. How big is N?
I think in one of the paper, because I was studying a lot, so I got the number 3000. But I don't know whether it was for this one or not. Because reading so many things, I was.
How about M?
M is the number of electrodes we are putting here.
And typically like
128.
Typically like how many of them?
128.
Oh,
They use like when for the data I received that had 16 electrodes, then 64 electrodes, 120 electrodes. So it goes like it has a fixed numbers.
Why is the dimension is important? Why dimension is important?
because it's just a sparse coding problem. Like, it's just a compressed sensing problem, so it's
So you find the sparse X given assumption of A.
yeah.
Excuse me, why you want to find this as a sparse for this problem?
Sparseness distributed. If we'll take it concentrated at a point, it means what will happen, we will not get the.
I
Like
guess
basically-
the assumptions may not even make sense, but
The thing is that we want more distributed kind of distribution,
No,
more
it's
sparse
not.
distribution. That suppose some
it's not actually. When you write down this equation, you basically assume S is, have lots. At least like you're looking for signal is not a lot of things going on. You said sparse distribution. What do you say again?
sparse means kind of what should I say? This is suppose a small area of the brain. Suppose, okay, I did some finger movement or some brain activity, any brain activity. So I want that I get the distribution as far as possible. I don't want that I get a rough estimation that it's coming from here. I want.
Is it the
No, I don't think so. I don't think the implication will be like that. You say like it's spread. Your distribution is kind of spread.
Means I'm talking. Suppose we take one part of our brain from where the signal is coming, and sparse means I got some signal because of activity. So I want the source distributed or sparse, not concentrated at one point.
No, actually, exact opposite. If you're doing the L1 long, you exactly get what you describe you don't want. You will get something like or like concentrate on some places. Like sparsely happen. of course, if you use the L2 norm, you will get something else. But if you use the L1 norm, you basically get something like just island, not spread around, but like here something somewhere a little bit and stuff like that. But I think everything up to now is very typical. I don't see anything special. And for the physical question, I guess the A you can generate by basically just solve those EM equations because you assume knowing the location, then you just compute if you given that, then the sensor will be here. So, okay, I guess we can continue.
The A is dependent on the location of the sensor in the
Yeah, depend on the sensor, location of the sensor and the location of the dipoles. You assume knowing where is the dipole, it's just like saying like how big is the dipole.
Because we have not just one A, we have A1, A2, and all of them. Each of them just end up there.
one of the sensors.
Yeah.
No. M is like the sensors. So then you have M sensors and M dipoles.
Exactly, yeah.
M sensor and
Yeah. Each A is
Here what he has suggested that the present study proposed a novel L1 norm electromagnetic source imaging algorithm by exploring sparseness in a transformed domain in order to reconstruct extended cortical sources. The thing is that he is trying to transform it. So specifically what he is doing, that each element in the transformed domain is calculated as the current density difference between each pair of neighboring elements on the cortical surface. Which what he is doing now, in place of suppose this value is S1, okay, suppose this value is S1. Now this paper proposed that don't take S1, take S1 minus S2, S1 minus S3, S1 minus S4. So each element in transform domain is calculated as current density difference between each pair of neighboring elements on the cortical surface. So the entire transform domain can be regarded as variation map of CCD. So earlier we were taking the current source as it is.
Everything okay?
So what he's proposed, in place of taking S, our target, he is trying to take the difference of S of the neighboring pairs. So the entire transform domain can be regarded as variation map of CCD, cortical current density.
Why you want to find it?
Because he said actually when we transform it, we will get the same advantage when we transfer the signal like in frequency domain. So by transferring from one domain to another domain, whatever advantage we will get those advantage here. So which is similar to those defined in other signal and image processing techniques. So he just used that technique.
What's
here.
the advantages?
The advantage will be like it will be more visualized. We can like when we change domain, we can see the different aspects of those signals. So that's why I think in place of finding out a different S1, S2 like the source signals is trying to take the differences of two neighboring pairs. That's what he is doing in this paper. That's called sparseness in transform domain. Here he has given the reason. If current density within each active cortical region is close to uniform, we expect sparseness in the transfer domain to largely occur on the boundaries between active and non-active cortical regions. If you can understand this point, this is an important reason why he is using this one. Suppose this is a reason, this is another reason. Okay? If current density within each active cortical region is close to uniform. So it means we are not finding any distribution, it's constant. We expect sparseness. Sparseness means clear difference in the transform domain to largely occur on boundaries between active and non-active particle regions. So in this manner we can see the distribution, which we cannot see in normal domain. In normal domain we can see the currents, which is uniform. But if we see in transform domain, we are finding out the differences. We can find out, oh, this is the active region, this is the non-active region, which can be identified by minimizing the Albert norm of variant match.
You have threshold for finding the non-active.
We are finding the difference of 2 points. So when active and non-active will be there is a boundary. So here the difference will come. In the active region, the current is same.
Yeah, I mean, what's the boundary?
Yeah, undoubtedly. There should be some active region, there should be some non-active region. So there, the visualization will be more clear than the normal domain.
Yeah, I mean that we just find the differential between all the S, okay? And to find the non-active and active regions. Okay, what's the bounds of that? You can just, okay, we have the differential, we can just find this one here, this one is here.
That's what means with the activity, what is happening? We are finding out some distribution in form of current. Okay, so at least we can find out, okay, current is generating in this area, current is not generating in this area. So this is active region, this is non-active region.
Yeah.
At least we can even find out in the like in CCD model, we can even find it out that current is generating here. We have some dipoles here. We are not getting some dipoles here, but when we change the domain, we will find out the difference. That difference will be clear. That if difference is 0 in this region and difference suddenly becomes a bag from coming from here, so it will clearly.
In non-active, the difference is 0. In non-active, the difference is 0.
In all the active thing, difference is 0. In inactive, it's 0. But from active and inactive, a clear boundary will be there because we'll get a big difference. That's why they use this variation. I request you give me more questions so that even I go into deep and like I assumed it as it is A. I didn't think how it will get it. So when I will discuss with you guys, I will get more points, what I have to study, what I have to go into depth. So this was the proposal. Let me check if I have those slides. Actually, I couldn't prepare this one. I will do it next time. This was what I prepared.
Oh, it's okay. It's okay. Oh. Can you write down the transform? Do they have a?
Yeah.
Maybe I.
They have here. In place of in the same equation, he used V. V is the transform.
They define the transform.
Stop it first.